So the question is how to get the topological rigidity. Let's explain the idea. The main idea is a compactness argument. That is, assume there is a sequence of embedded closed surfaces in three-dimensional Euclidean space passing through the original point. Then, if we also have the Willmore energy is strictly smaller than 32 pi, and their mean curvature is close to a constant in the L2 sense, and the volume is normalized to be 4 pi. We expect that the sequence of surfaces will converge to a limit surfaces which is immersing in the Euclidean space with constant mean curvature. The normalization of the volume guarantees the mean curvature is 2 pi, and as we explained above, the non-degenerate condition will guarantee this limit surface to be embedding, which means the limit is the sphere by Alexander of the rigidity theory. Furthermore, we want to show our convergence is strong enough such that the sequence of surfaces is homomorphic to the limit, which means the surfaces is are all homomorphic to a sphere. That is the topological rigidity. So for this convergence, we need a compactness result. That is my joint work with Jianxin Sun in 2022, which says if there is a sequence of surfaces properly immersion in the Euclidean ball with radius r and passing through the original point, if the sequence of surfaces has a uniformly bounded area and their total curvature will not concentrate, which means the L2 norm of the second fundamental form of the sequence of surfaces is smaller than some epsilon 0. Then after passing to a sequence, we have two kinds of convergence. Firstly, in the intrinsic sense, there exists convex surface sigma with base point P and continuous metric G, such that there exists a parametrization in phi I from the limit surface sigma to the surface sigma I, such that the pulling back metric of the matrix of sigma I will converge to the limit metric in the LQ sense for any q smaller than infinity. That's the intrinsic convergence. And secondly, we also have the extrinsic convergence, which means there exists a proper asymmetric immersion of the limit surface to the Euclidean space with the same radius, such that after composition with this parametrization, we have the sequence of immersion convergence to the limit immersion weakly in W22 and strongly in W1Q for any Q smaller than L infinity. Here are also some remarks about our compactness theory. Firstly, we have more information on the sequence of metric. In fact, locally we can write the sequence of metric conformally to the Euclidean metric with in a disk with uniformly bounded radius, and the conformal factor is also uniformly bounded by some C. Secondly, we want to explain the key condition in our compactness result is the long concentration of the total curvature, which means the square integral of the second fundamental form is smaller than some epsilon 0. This is scaling invariant. Thirdly, we want to explain the above local version of compactness theory can be glued to be a global one, which means if we have a sequence of closed surfaces in the Euclidean space with uniformly bounded area and non-concentrated second fundamental form, then we have the sequence of surfaces convergence to some limit. Finally, we want to explain our W22 convergence or W1Q convergence for Q large enough is embedded in C alpha convergence. This is strong enough to for topological rigidity. But there is also one question remains, that is, in our setting of quantitative rigidity for L2 almost constant mean curvature surface, all the conditions are about the mean curvature, but in our compactness result, we need the long concentration information of the second fundamental form. So how to translate from the condition on mean curvature to the condition second fundamental form? There are still some works to do. Let's first the first is to localize our long concentration condition. That is the following lemma, which says if we normalize the area of the surfaces to be 4 pi and assume the sequence of the surface has Willmore energy is uniformly smaller than 32 pi. If the mean curvature is close to a constant in the L2 sense, then the Willmore energy will not concentrate, which means when I is sufficient large and R is sufficient small, the Willmore energy will also be in the ball BRP will also be very small for any P belongs to sigma I. Moreover, we have that for any gamma strictly smaller than alpha, there exists some constant A such that the error ratio in the scale of R smaller than A is strictly smaller than 2. In fact, it is smaller than 2 times 1 minus gamma for any P belongs to sigma I and I sufficient large. What does this mean? We have some explanation. We call this localization of the long collapsing condition because in global our condition on the strictness smaller than 32 pi of the Willmore energy will exclude the touching of two spheres or more spheres at a point. So we call it global long collapsing condition, but just as we see in the picture, the global collapse will always happens if in local there is a neck which looks like a cataloid. Notice that the cataloid has density 2 at area density 2 at infinity. So in local we use the error ratio to to describe the non-collapsing condition. That is the strictly smaller than 2 of the error ratio will exclude the collapse in local. So we call the above lemma the localization of non-collapsing condition. But another understand of this lemma is this concluding this concluding comes to the critical case of Allard regularity theory, which means the square integral of the mean curvature is small and the error ratio is strictly smaller than 2. For Allard regularity theory, it is an important theory in geometric Meyer theory, which says that if V is rectifiable and variable, we can imagine it just as a manifold in the unit ball of Euclidean space with the original point path belongs to it. Then if we further assume the volume of this variable in the Euclidean ball is smaller than 1 plus delta times the standard volume of the standard disk, and the mean curvature is small in some supercritical case, which means the mean curvature, the LP norm of the mean curvature is smaller than delta for some supercritical case P greater than the dimension n. Then after rotation, the support of this variable will be written as a graph near the neighborhood of the original point. Moreover, the graph is the graph function U has the C1 alpha regularity for alpha equals to 1 minus n over p. This is Allard regularity theory. In the viewpoint of partial differential equation, when we regard a manifold in Euclidean space as an immersion, then its mean curvature is expressed by the Laplacian of this immersion. So by comparing with elliptic estimate, if the mean curvature belongs to LP, then the immersion or the submanifold itself belongs to W2P. But note that the Laplacian is taken with respect to the pulling back metric G, which itself depends on the immersion F. So the right-hand term is a nonlinear depend on the F. So this is a nonlinear equation, which needs Allard need to assume the supercritical index P is strictly greater than the dimension n to get a decay estimate and get the Allard regularity theorem. But just as we say, we just have the critical case, which means our mean curvature is integral in the L2 sense, which is exactly equal to the dimension. So we need some kind of critical version of Allard regularity theory. There is some result when I was research the topology of surfaces with finite Willmore energy, which says that for a rectifiable two variable passing through the origin point with small value and Willmore energy, a lot of Willmore energy. The square integral of this surface, the square integral of the mean curvature of this surface is more than delta. Then, in a small neighborhood of this support of the varifold, this varifold is biholder equivalent to a disk, a disk of some plane T. But I need to say this C alpha, this biholder equivalence regularity is not enough to guarantee us to get information from the mean curvature to the second fundamental form. Not like the case of the Allard regularity theorem, which has a supercritical case, because in the supercritical case, with this C1 alpha estimate, Dugan can write down the mean curvature equation under the graphical coordinate and show that the graph function u is in fact belongs to W2P, which implies the LP norm of the second fundamental form is also very small. But as it is seen, the graphical coordinate under the graphical coordinate, the mean curvature equation has coefficients involved the gradient of u, which means if we want to leave the regularity, we at least need the Lipschitz estimate. So the C alpha estimate is not enough, but and we need some more works. That is our key observation. This is called the optimal regularity for the critical Allard regularity theorem, which says for any epsilon greater than 1, there exists delta and A such that if a surface is properly immersed in the Euclidean ball and pass through the original point, and the volume of the surface is strictly smaller than 2 times of the area of a standard disk with radius 1, and the square integral of the mean curvature of such surface is smaller than delta. Then, for some radius sigma, we have the long concentration of the second fundamental form in such a radius, which means the L2 norm of the second fundamental form in a ball with radius sigma is smaller than epsilon. Moreover, there is a conformal by Lipschitz homeomorphism phi from the disk with the same radius to the surface, such that the Purnian back metric is conformal to the Euclidean metric with conformal factor small in the C0 sense. Anyway, we have get the long concentration of the Willmore energy to the long concentration of the second fundamental form, and we can use our compactness result. Finally, let me conclude our ideas. That is, if we have a sequence of surfaces with Willmore energy strictly smaller than 32 pi and mean curvature close to a constant in the L2 sense, then by our localization of this non-collapsing condition, we can get the critical condition of Allard's regularity theory. So by using our key observation, the optimal regularity for critical case of Allard's regularity theory, we get the non-concentration of the second fundamental form. And thus we can use our compactness theory to get the topological rigidity of the sequence of the surfaces. Finally, with this topological rigidity, by Deninis and Mueller or Lam and Schattler's quantitative rigidity for L2 almost umbilical surfaces, we get the conclusion. That is my talk. Thank you.